Hello everyone, welcome to this talk where I speak about private computation of polynomials over networks. My name is Teymur Hossein Alizadeh, and this is a joint work with Fatih Turkman and Nima Munshizadeh, all from the University of Groningen. We can argue that computational power limits were the main reason behind developing distributed algorithms. But right now, with the rise of cloud computing and broadband communication, this is not a major problem. However, privacy concerns play a significant role in developing distributed algorithms. But unfortunately, distributed algorithms themselves cannot entirely solve the problem of privacy for the agents that are involved in those algorithms. In this work, we present a solution for this problem. We can classify the literature of privacy in control system into three main categories. The first category belongs to differential privacy-based methods. Differential privacy is information theoretically secure, but there is usually a trade-off between privacy and control performances, and also there is a vulnerability of data disclosure by least significant bit. System theory itself also provides solution for the problem of privacy. Methods in this category preserve performance of controllers, and also they are lightweight in computation. But their privacy guarantees are much weaker compared to differential privacy and cryptography-based method. And also they are highly problem dependent. The third category of the method belongs to cryptography-based methods. We can classify the methods in this class into two categories. The first one belongs to the single agent case, where a system outsources the computation of a linear controller or an optimization to the cloud. The next category belongs to the multi-agent system, where our study also belongs. In this category, we can talk about consensus over undirected or directed graph, and also distributed optimization and the problem of linear controllers in multi-agent system. With respect to this literature, our algorithm does not need a central party or a third party while the agents run our protocol. And compared to this study, our proposed protocol can afford evaluation of polynomials instead of the affine functions. In our work, we assume a network of M agents connected through an undirected graph with this node set and this edge set. Also, we use Pylier as a partially homomorphic encryption with its three main steps: generation, encryption, and decryption. As we know, Pylier is additively homomorphic encryption, and also it only accepts non-negative integer in its domain. So we need an encoding and decoding because we work on the real number. Also, we use this notation for the encryption of a value such as X by public key of agent I. We also use threshold secret sharing, where a third party shares a secret S among n agents, while T of them are required to recover the secret. We assume that agent I in network G is interested in evaluating this polynomial. As it is clear, this polynomial is a function of agent I private value and her neighbor private values. And it has two main parts, a bivariate and the multivariate parts. As an example, assume that agent 1 in the network with three neighbors, 2, 3, and 4, is interested in evaluating this polynomial. In this polynomial, P12, P13, P14, and W1, 2, 3, and 4 are chosen as it is required in 1. We also have two main assumptions in our work. Agents in the networks are honest but curious. And also the adversary A is PPT, passive, and present in the communications. By having 1 and the assumption, we formulate the problem as providing a privacy-preserving protocol for the evaluation of 1 for agent I. In this section, I present our proposed algorithm. Our algorithm has two main phases, offline and online phase. In the offline phase, We assume a third party selects addition and multiplication shares from this set, such as 3a and 3b holds. Omega is a publicly known and sufficiently large prime number. Also, the third party distributes addition and multiplication shares among the agent I and her neighbor. We also point out that the addition and multiplication shares can be generated distributedly. This means that we can get rid of the third party and run the algorithm completely distributedly. Before presenting the online phase of our algorithm, we point out the existence of a distinguished agent among the neighbors of agent I. The roles of this agent becomes clear at the step 5 of our protocol. Also, as a running example, we consider agent I with her neighbor who are interested in evaluating phi1. Again, we assume that before the online phase, at step 0, all the agents have already received addition and multiplication shares. In this part, I present the online phase of our algorithm. At step 1, agent I chooses the public and private key of Pylea. Then she publishes the public key. She also sends a form of the polynomial Pij and Wj to her neighbor. In our running example, this means that agent 1 informs agent 2 of the form of P12. This means that agent 1 informs how x2 appears in P12. Step 2 is also done by agent I, where she encrypts and sends this value to her neighbor. Also, she computes mu I. Notice this value is the private part of agent I, which appears in Pij. In our running example, this means that agent 1 encrypts x1 to the power of 2, which is this part of P12, and then sends it to agent 2. She does the same thing for agents 3 and 4. Step 3 of our algorithm is done by the neighbor of the agent I. This means that they encrypt the addition share and evaluate 4a and 4b, and then sends sigma j and mu j to agent I. In our example, this means that agent 2 and 3 compute sigma 2 and sigma 3, which amounts to evaluation of P12 and P13 over ciphertext, and also mu2 and mu3, and sending them to agent 1. Notice that in our running example, we consider agent 4 as a distinguished agent. Step 4 of the algorithm is done by agent I, where she computes psi I and then sends the encryption of it to the distinguished agent. In our example, this means that agent 1 computes psi 1 and sends the encryption of it to agent 4. Notice psi 1 amounts to the multiplication of W1, 2, 3, and the multiplication shares. Step 5 of the algorithm is done by the distinguished agent, where she computes 4a and psi j and sends the multiplication of them to agent I. In our running example, this means that agent 4 computes sigma 4, which amounts to evaluation of P14 over ciphertext, and sends it back the multiplication of sigma 4 and psi 4 to agent 1. Step 6 of the algorithm is done by agent I, where she decrypts sigma j and this multiplication to get 5a or 5b. Step 7 of the algorithm is done again by agent I, where she adds 5a, 5b, and the addition shares to get this value, which after decoding is phi I. In our running example, this means that agent 1 decrypts sigma 2 and sigma 3 to get P12 and P13, and also decrypt sigma 4 times psi 4, and aggregates S1a to get the final value phi 1. In this section, I present the privacy analysis of our algorithm. First, notice that the privacy of agent I is preserved because she communicates with her neighbors through Pylea, and we know that Pylea is computationally secure. The case for the neighbors of agent I is also interesting. For studying the privacy for the neighbors, we consider two sets, the set of corrupt and non-corrupt agents. The set of corrupt agents shares their information with each other. There's a theorem in our paper which states that as long as the distinguished agent is non-corrupt, the privacy of an agent such as agent J is preserved. Also, we comment that the distinguished agent can be corrupt, but in that case, agent I is able to find the exact value of the summation and multiplication part. In our running example, this means that agent 1 finds out the exact value of this part and this part. For the simulation case, we consider a scenario where agent 1 with her neighbors has this dynamic. We designed a controller based on feedback linearization. Notice that the private variables are x1, x2, x3, and the coefficient. Our goal is to privately evaluate U. We consider the sample time for the controller as 1/3 and 1024 bits for pi layer and 200 bits for the public value, omega. We run the algorithm on a machine using Python. Our simulation results show that the algorithm is correct, meaning that by running the algorithm and on plain data and also on the ciphertext, both dynamics converges to the origin exponentially. But we see that it is computationally demanding. This means that with the increase of the key lengths, the computation time increases. This makes the algorithm suitable for applications where the sample time allows this amount of computation. In this presentation, I talked about the importance of privacy in distributed systems, and I presented a protocol for evaluating polynomial based on a partially homomorphic encryption and secret sharing. I also presented the privacy analysis of our algorithm. We extended the result in this work in numerous directions. First, we considered the privacy issue in network games. Also, we extended the algorithm for evaluating a general polynomial. We also use pseudo-random functions for generating the shares in a distributed way. We also address the privacy issue of coefficients in WJs. And we presented the secure computation and system theory proofs for the algorithm. Thank you very much.